Okay, today I want to talk about the invariance under the deformation retract. And this theorem is all about first we'll let M be a smooth manifold and sigma be a submanifold of M. And then if sigma is also the deformation retract of M, then it implies that the first Dirac cohomology group of M isomorphic to the first Dirac cohomology group of sigma. To start the proof, we need to define something necessary things, just like a C1 family of smooth map, which called the psi T, which is mapped from the M to sigma. And then we satisfies those three conditions or three properties which define it from the deformation retract. So we can see that the psi T map will map from M to sigma, this submanifold, which will also induce a pullback map from the Dirac cohomology group of sigma to the Dirac cohomology group of M. So in order to show they are isomorphic, we need to find an inverse function of this psi, the pullback of this psi map. So because there we are finding it involves the submanifold, naturally we will think of the inclusion map, such that from a sigma map to our manifold M. In other words, it will also induce a pullback map from the first Dirac cohomology group M maps to the first Dirac cohomology group sigma. We can see that those maps have an opposite direction. So now we want to show the pullback of the inclusion map is the inverse of the pullback of the psi map. Then we can show them they are isomorphic. So now then we can start the proof now. First, we need to let omega be an arbitrary closed one form defined on M. And then there exists a scalar function f from the manifold to the real number. It will define as fx equal. We will integrate this omega from this psi map. To understand this integral, we can treat this psi map we got as just a curve with parameter t. Such that with joining the psi 0 from x equal to x to the precise one, x belongs to sigma. So we can just say that it is just a line integral from the point x and then along to this line to a point from sigma. And now, just in this part, we will just assume x belongs to the manifold, but x does not belong to the manifold sigma. And another more important assumption is the precise curve is covered by only one parametrization. This is just only one parametrization is just a special case, but it will help us in later. Okay, when precise curve is just covered by only one parametrization, it also means that we can just use only one local coordinate. And then we will just define it per u1 to un. So omega will equal to the from I equal to 1 to n, and express it by local coordinate. Now we will transform this integral under our local coordinate, and what is our main result is we would like to show that from this integral to show the following result. The precise star and the inclusion, they are just an identity, such that when we applied a differential form under an equivalent class, it is just themselves. After expressed under the local parameterization, it will change it from the 0 to 1 as t belongs to 0 to 1, and then just break out everything down in local coordinate. So yes. Right. And omega I is also along the precise curve, this curve. And then by chain rule, because the symbol of this part is just we want to change the precise curve is also can be expressed in our local coordinate, and to express the ui coordinate of a precise, which is we will define it as the precise ti, which also means that it's just a composition. Then, by taking the derivative, take exterior derivative, dfx by definition. We take the j component. Since it is finite, so we don't need to worry about to take this summation out of the integrals. So we'll just put the I come out also, and then from this integral, differentiate everything by uj to this stuff. And then duj. So by the product root, we will get that first we will differentiate this thing and then keep this thing, and then we will just differentiate this stuff and then keep this stuff. So let's copy down everything. And by the chain rule, we will just break out and add the summation part. Such that make I the UK and then put the side here. Differentiate this stuff, and then we will just differentiate the psi map inside the omega, and then add this thing back here. Differentiate each coordinate from the tree diagram, and yes. Then by the product rule, just copying the whole thing here. And then everything with the duj. Yeah. So since about omega is closed, so we can interchange the index from the denominator to the numerator. So and then we can rewrite it as we can just rewrite the exterior derivatives by just copying the everything out here. But this time with a different coordinate. So after the change, we can find it by observation. We'll just see it after just put our I inside back to the integral. We'll just find that it's just an antiderivative with respect by t of this stuff. Then by just taking out and integrate, we will get the following result. But what's that? What does this stuff mean? That so we will just, and now we can check that from the inclusion map. Because we will think that when we back to this photo, because in each point, just like maybe this part, we will just maybe it at t equal to 0 and each part is t equal to 1, and here is t equal to maybe just something just like t log. When if there has a just something just like invertible map here, so the inclusion map will also depends on t, because from each point which of the beside this point its inverse should also depend on t. So we will just label the outer t, and so we'll make that the inclusion map is also depends on the t from the point of the result under this the precise transformation, and then to the map back to the M. Then we can check that those pull back and induce stuff. Which is by the chain rule, and by the chain rule we can find that it's just a composition of the omega k duk. And then we'll just put all of this up, add on here, and then add on the differential form also, and then by the definition we will get the following stuff. The omega k will in terms of the RT, the outer t, and to the side t, and the omega, and then we can just put the pullback inside the d. So by definition we will just got this. And then it will just form the following things. And then by chain rule we can find that this thing under the chain rule we can just expand it out, and then to become the beside t of k, and d respect by the uj and duj. and this stuff is exactly this thing. So we can just substitute this definition, the expression, into this part. And then we will just call this result. And then it's the following thing. Since we know that when t equal to 0 of x, we will just give feedback the x here. So the precise is just an identity on M. Since it is just from the x map to the x, when we talk about the inverse, the outer 0 of x is also just outer is just equal to the identity which is on the manifold M. Okay, so now we just proved this result from this assumption by just precise t only covered by only one single parameterization. So now we need to consider what if precise t is covered by many parameterization. Different parameterization. Because the precise curve will be just covering by finitely many local charts, so we need to show that it is because of we are using a compact manifold, so the precise tx is we can just keep by constructing a partition from 0 to equal to 0 naught. Under from 0 to 1, we can just chop from different parameterization and just chop different time intervals, and such that the precise this map is restricted to the t per time belongs to t alpha minus 1 and t alpha. They are just only well defined, will be restricted in each partition, and which is by only one single parameterization. So since the precise t, this curve is compact, so we can find there is finite subcover to just cover the whole precise t curve, and we can just restrict it from each. There is have only finite interval, and then just chop this from 0 to 1 and just chop there is finite partitions, and we just restrict to each partition can be just covered by only one single parameterization. Then we can use the result from this formula, from this equation, by just taking the summation of each finite parameterization, this finite chart. Then by rewriting the scalar function, and with the local coordinate, and then by using this formula, we can just we take this differential, or I mean take the exterior derivative of this scalar function. Actually, it's just the summation alpha 1 to the end, and then just quoting the result from the previous thing. And then when we can see that there will have many cancellation, just like from this one and this one and this one and this one, just 0, 1, and then -1, and 0, 1 minus 0, -1, there's 2 here, and then -2, and then 3 here, and after the cancellation, it will remain this condition. It will just remain to give out exactly the same result. So, and this completes the proof of it in the general case. And in order to complete the whole theorem, because in the beginning we just assume that the x belongs to the manifold, but the x does not belong to sigma. We know that under this precise map, if x in the sigma already, then the precise map will just holding it together. So the outer is still from sigma map to the sigma. Okay, to complete the proof, we now just assume x belong to the sigma, and then we will connect let eta be an arbitrary one form eta on the sigma. We want to claim that the sigma by this pullback map it will just give me the eta here. So we will use by using the local coordinate on M, just like we were just using the previous, the U1 to the UN coordinate. Then by immersion theorem, as sigma is just a submanifold of M, so we can claim that for every point on X, for any point on X on the sigma, we can find an open set such that we can by using the spatial coordinate system, just like to 0. Then we can just denote that the eta using the same coordinate system, just like the same coordinate system of our manifold. And then sec eta is equal to by express it into our local matrix, local coordinate from 1 to the k, just like this one. After taking the psi map of it, by just pulling, by definition, we just putting the psi, this pullback map into the scalar function and also the differential form. And then by definition, it's just if I is indexed, and then by the chain root, we will get the following result. Since the psi map from 1 of x is equal to x, as x is inside our sigma, so we will also know that the sigma 1 of I of x is equal to the xi. I mean the ui of x, the ui coordinate of x. Therefore, by just taking this idea, we will get duj. Actually, it's just taking the I coordinate of x of duj, so it's just delta ij. Then it will just simplify it to delta I equal to 1. And then it's just the differential form, and then so it's just eta. So there is no change under this. You can see that there is no change under this induced precise map, induced pullback precise map. So in other words, under those mapping, these two composition of the two pullback map, the eta is still inside the sigma. So combining this result, Comparing this result and this result, we can see that the pullback of iota and the pullback of the psi map, they are the identity on the first Dirac cohomology of sigma. And for the another direction, it is equal to the identity on the first Dirac cohomology of the manifold M. As the result, they are the pullback of the psi map is and the pullback of the inclusion map, they are the inverse to each other in the first Dirac cohomology group. So therefore imply that the first Dirac cohomology group of M is isomorphic to the first Dirac cohomology group of sigma. And this finished the proof.